Hi, I'm Vicky Scowcroft, and today I'll be talking to you about the work I've done with the Spitzer telescope as part of the Carnegie Hubble program, going from Cepheid to supernova to measure the Hubble constant. I'd like to acknowledge some of my collaborators initially. Wendy Friedman is the PI of the program. Barry Medore and Eric Persson are senior members of the team. Andy Monson, Jeff Rich, and Mark Seibert are all postdocs. Also at Carnegie, and Jane Rigby is now at NASA Goddard. So the first question people often ask when I say we're measuring the Hubble constant is, why are we still doing that? Surely we measured the Hubble constant already. But the problem is that the Hubble constant at any given time has been known to 10%, despite having changed over that time by a factor of 10, which obviously isn't ideal. So if we look here at this plot compiled by John Hooker and Craig Booth, you can see how the Hubble constant has changed over its lifetime. So in the 1930s, we had values ranging between like 300 and almost 1,000. And then as you go into the 50s and 60s, the value is decreasing. And from like the 60s and beyond, the value has tended to converge down towards between 50 and 100. And the different colours in this plot represent the different techniques that were utilised to measure the Hubble constant. So now if we zoom in to the last 10 years or so of measurements, you can see that we really tend to be converging towards a single value of around 70, 75. You can see that we're still utilising a number of different techniques, but particularly in the last, since 2010, the error bars are becoming so small on these measurements that the measurements aren't actually consistent with each other anymore. Although we are converging towards a value, the error bars from the different techniques mean that the measurements don't overlap. So that's now becoming a problem, that our measurements from techniques such as the distance ladder don't overlap with measurements that come from things like the CMB. So the reason we really want to understand the Hubble constant is not necessarily because we want to know the value of the Hubble constant itself. We know that the universe is expanding. We have a general idea of how fast. But as Wayne Hu said in 2005, the single most important complement to the CMB for measuring the dark energy equation of state at a redshift of a half is the determination of the Hubble constant to better than a few percent. So you can see in these plots here where we're relating different cosmological parameters to each other. So on the left-hand plot, we have the dark energy equation of state and then a density parameter. That as you have a range of each of these parameters, we need to constrain these ranges to get a better value for each of the parameters. And what's interesting is that the uncertainty on W tends to be double the uncertainty on the Hubble constant. So if we could decrease the uncertainty on the Hubble constant to 1 or 2%, then we could also decrease the uncertainty on W, which would give us better estimates of the other parameters of the cosmology of the universe. So there are two main techniques we use to measure the Hubble constant, and these can be classified into the distance ladder techniques and geometric techniques. So the distance ladder uses standard candles to estimate distances. When standard candles are objects that we know their intrinsic brightness, so we can determine their distance from how bright they appear to us. So the distance ladder uses different techniques tied together at each level. So initially we have Cephids, and then we move out to a different distance measure which is calibrated by Cephids, and then move out these different steps. The problem with distance ladder techniques is that because we're looking at luminosity distances, things like reddening and extinction could be an issue, as well as different compositions in different populations. And what we found is that the Hubble constant measurements from distance ladder techniques tend to give higher values of the Hubble constant. On the other hand, we have geometric techniques, which use a standard ruler to estimate distances. So instead of saying we know the brightness of something, we say we know the absolute size of something, and then we can tell how large that appears to us and work out its distance. This is a single technique instead of lots of different techniques tied together, which you'd think would be better as it eliminates systematics of tying different things together, but it's model dependent. It depends on your model of the cosmology of the universe. And in this case, we tend to get lower values of H0 compared to the values from the distance ladder. So the Carnegie Hubble project that I work on is a distance ladder technique. So what we want to do is get from the Earth to the Hubble constant at the top of the ladder. So our 0 point for the distance ladder is 35 galactic Cephids, which are calibrated by parallax. So 10 of our Cephids have parallaxes from the Hubble Space Telescope, when these are the most accurate parallax distances available. So once we have those distances from the calibration from the galactic Cephids, we move out to the LMC, where we have 85 Cephids. And we use those to confirm the slope of the Cephid period luminosity relation and to measure the distance to the LMC. Once we've got the LMC, we can move out into the local group, where we have 14 populations of Cephids. And these range in metallicity, range in reddening, and other parameters, and then we can use these local group populations to assess the effect of systematics from things like metallicity. Once we go beyond the local group, we have 9 populations of Cephids further out. And this is where we start to include other distance indicators. We have NGC 4258 in this population, which has a maser, where we can get a geometric distance to this galaxy. And we also have M101, which had a recent supernova. Beyond the local group, we have 404 galaxies with Tully-Fisher relation measurements. And some of the local group galaxies we've studied are used as calibrators to calibrate the Tully-Fisher relation distance scale. And further beyond this, we have 44 galaxies which hosted supernova, which we have measurements of. The great thing about this program is it all uses a single instrument. This is all using Spitzer and all using the IRAC camera. And it's all been done as part of the WARM mission. So we have no systematics from using different instruments or using the instrument in a different mode. This is all a single instrument program. So the reason we're using Spitzer is because it operates in the mid-infrared. In the mid-infrared, dust is practically opaque, so we practically eliminate reddening and extinction. Again, as I said, we're using a single telescope which eliminates any instrumental systematics from different systems, and we believe we should be able to reach an accuracy of 3% using warm Spitzer. So in here you can see the difference between what a galaxy appears like in the optical and the infrared. You can see that we're seeing different features of the galaxy and the dust has become opaque. So the way we measure distances with Cephids is using what was known as the period luminosity relation. The period luminosity relation was first noted by Henrietta Leavitt in 1912 when she was studying the Small Magellanic Cloud, and she was looking at these Cephids and noted that the brighter variables have longer periods. So you can see in this plot on the right-hand side that the period luminosity relation for a load of different Cephids in the, I think this is in the LMC, where we've looked at the Cephids from the U-band, right in the very blue end of the optical, all the way through the optical, the near-infrared, and through to the Spitzer bands in the mid-infrared. And what you can see is that the slope of the relation becomes steeper as you go to the infrared, and the dispersion around the relation becomes much smaller. So in the infrared, we can get a much more accurate measurement of the distance of a Cephid just by the nature of the relation being much tighter in the mid-infrared. So this is why we focus on the mid-infrared for Cephids. Now in 2009, there was a resolution passed at the IAU to recognise Henrietta Leavitt for her work on the period luminosity relation. Because at the time, she was hired as a Harvard computer, so she did the work while other people published her results. So rather than referring to the period luminosity relation as the period luminosity relation, it's now known as the Leavitt law. So any papers you see now will say the Leavitt law rather than the PR relation. So our initial calibration was with local Cephids. As I mentioned, we had 35 galactic Cephids, which calibrate the period luminosity, the Leavitt law 0 point, and 85 Cephids in the LMC, which calibrate the slope. So this is a selection of our light curves of our galactic Cephids. And you can see here that these light curves are just exquisite. The amplitude on the light curves is very small. Y off in the upper left-hand corner has an amplitude of around 1/10 of a magnitude, and you can still see great detail in this. You can see detail that shows up in both bands, showing that this isn't a photometric effect. This isn't uncertainty introduced by a reduction. This is actual fluctuations in the light curve that Spitzer is measuring. And we've never had light curves of this quality in the mid-infrared before. The bottom curve, so the top two curves are 3.6 and 4.5 microns, Spitzer's IRAX channel 1 and 2. The bottom curve is the difference between these two bands, so the mid-infrared color. And you can see there's this variation through the cycle. Now, when we designed this program, we wanted to use both 3.6 and 4.5 to measure distances. And we thought that the color would be flat and constant, would be constant and zero through the cycle of a Cephid's pulsation. But as you can see, it varies through the cycle, its amplitude varies, its shape varies. And what we've discovered is that this is due to CO in the Cephid's atmosphere, and as the Cephid changes in temperature throughout its pulsation cycle, the CO becomes dissociated as the star gets hotter and breaks up, and that allows more light to flow through the 4.5 micron region. And then as the Cephid cools down again, as it gets bigger, the CO recombines, and that blocks the 4.5 micron light from escaping, and that induces this temperature change. And this was never known about before. This was all discovered during the Spitzer program. And what we think is that as we've analysed this in different galaxies, we think that we can use this as a photometric metallicity indicator with an uncertainty similar to that of spectroscopic metallicity measurements. And this was all discovered by Spitzer in the last 4 years. So when we had the calibration from the galactic Cephids, we measured the distance to the LMC by comparing the samples in the LMC and the Milky Way. And here you can see our plot that was taken from the Spitzer press release. The blue points are the Cephids in the Large Magellanic Cloud, and the yellow points are in the Milky Way. And you can see the dispersion around this is really small. And it gave us an uncertainty on the distance of the LMC of 0.03 magnitudes, which is excellent. This is a really small uncertainty. We've really, using a single instrument on Spitzer, has minimized our systematics dramatically. And this is a great measurement. Recently, it's been confirmed independently by a group that measured eclipsing binaries in the LMC, and they measured the distances to those systems. That's a geometric measurement rather than a luminosity measurement, and they get exactly the same answer. So we've now confirmed this result. So with the new measurements of the Leavitt law and the new calibration with Spitzer, we could reanalyze the results from the Hubble Key project, which was done a decade previously with the Hubble Space Telescope in the visual. So they had the same aim to measure the Hubble constant and minimize systematics, but they did it in the optical. And by moving to Spitzer and the mid-infrared, we managed to dramatically reduce the uncertainties. So the blue bars in this plot are the Key project uncertainties from each of these components, and the red bars are the Spitzer uncertainties. And you can see we've really managed to bring those down by moving to Spitzer. And we find a Hubble constant of 74.3 with a systematic error of 2.8, which is one of the most accurate and precise measurements to date of the Hubble constant. It's consistent with other measurements from other groups, such as Adam Rees's group, who did similar measurements in the H band, and we're really starting to drill down into the systematics of the Hubble constant. So the next step was to move further out in the distance ladder using the Tully-Fisher relation. And for this, we combined with the Cosmic Flows team, who had their own program on Spitzer, and have their own independent program to bring the two groups together. So for the CHP program, we had 404 galaxies with the Tully-Fisher relation. We have 44 supernova hosts. So the first thing we had to do is calibrate the Tully-Fisher relation in the 3.6 micron band. So here we had 26 galaxies that are our 0-point calibrators, where we have independent distance measurements. And we relate the line width to the magnitude to calibrate this relation. And then we apply it to a selection of different galaxy clusters. And here the different colours represent the different systems. What's interesting is when we did this calibration and compared it to the calibration in the I band, the 3.6 micron Tully-Fisher relation actually has slightly higher dispersion than in the I band, meaning we can't get quite as accurate distances. And this was puzzling. We thought that as with other Cepheid measurements, the dispersion should decrease because of the lack of dependence on reddening and the lack of metallicity effects and population effects. And even when we add in color corrections, our IRAC Tully-Fisher relation still has a larger dispersion. So what we actually put this down to is that in the mid-infrared, like when you're looking in the I band at a galaxy, you're seeing a certain population of stars. When you go to the mid-infrared, the AGB stars that were previously quite faint in the I band suddenly become very, very bright, and they're adding to the total light that's present in the galaxy. So now you've got a different population, which does have, and the AGB stars do have more population effects on their magnitude. So you're seeing that dispersion in there. So unfortunately, the 3.6 Tully-Fisher relation is not as tight as the I band, but by the fact that we're sticking with a single instrument calibration and we're removing systematics that way, cancels out the effect that the dispersion is slightly higher than in the I band. So it's not a big problem. So we can measure the Hubble constant from the Tully-Fisher galaxies. To do this, you measure the velocity of the galaxies and the distance. And we recalibrated the 0 point of the distance scale, in this case, to use our distance to the LMC that we derived previously. And we get a very consistent value for the Hubble constant. All that does is with the 0 point calibration is just set the 0 point. It's not setting the difference in distance of these galaxies. So we're finding a consistent result. It does have a slightly higher uncertainty, systematic uncertainty, but that will be reduced as we add in more galaxies. So the next step to improve our distance scale is to move to the local group and beyond. This allows us to investigate systematics like metallicity and to improve the calibrated distances that we have for the Tully-Fisher relation. So the first galaxy we looked at for this was IC 1613. And IC 1613 has really low internal reddening. This is why it's been studied for the last 50 years. It has really low reddening. So if you look at Cepheids, then you should be actually seeing them as they are. And it also has an extremely low metallicity, even lower than the SMC. So this is like the extreme end of our metallicity case. If we were going to see a metallicity effect, we would see it here. So what we did in this case was slightly different to how we treated the LMC in the Galaxy, is that we stacked all the data we had from Spitzer into one image. And because Spitzer is so reliable and its calibration is constant and it doesn't change, when we stack all this data, we're essentially averaging over a light curve of a Cepheid without having to reduce each image individually. So this gives us a higher signal to noise on the resulting magnitude and an average over the light curve immediately by just analysing one image. So the plot on the left actually shows our stacked image from Spitzer, and you can see the pink circles show where the Cepheids are located. So what we did, we had the IRAC data, and then we combined it with new data, near-infrared data from the 4-star telescope, and then went through the literature and found Cepheid measurements in the optical bands. So now we have 9 bands of data on Cepheids in this galaxy. And when we plot these as a function of inverse wavelength, we can fit the reddening law using the inferred distance modulus and the inverse wavelength. And we determined a very small reddening, as we already knew was true, and got a distance modulus of this galaxy of 24.29 with an uncertainty of 0.03 of a magnitude. This is consistent with other distance measurements, both from Cephids and from other distance determinations, and is one of the most accurate distances to date. Again, all enabled just by using the unique properties of Spitzer, that it's in the mid-infrared and it's constant. So the next step of our program is the Carnegie Auroral Lyrae program, where we want to look at auroral Lyrae stars as opposed to Cephids. So auroral Lyrae stars are population 2. They're very old stars compared to Cephids, which are population 1. So this is like complementary to the CHP. And now we're looking at a different set, completely different population of stars, and we should get an independent distance calibration. We were awarded 800 hours in cycle 9 to study this. So now we have a combined distance ladder. Again, we're starting from the Earth and going up to Hubble at the top of the ladder. So we have our original calibration with the galactic and LMC Cephids. But now we're adding in galactic auroral Lyrae. There's a very large sample of auroral Lyrae in the galaxy from the Hubble survey. So we have some that are calibrators that we use to measure the initial period luminosity relation, and then we have a large selection over the whole galaxy. We also have a large number of globular clusters, which are known to host large populations of auroral Lyrae. So we can measure the distances to these globular clusters very accurately with the auroral Lyrae. The overlap point is the local group, where the local group has galaxies that host both auroral Lyraes and Cephids. So we're going to look at the LMC again and other local group galaxies where we can measure the distance with both Cephids and auroral Lyrae. Then the rest of the distance ladder is the same, back up to the Hubble constant, because we can't actually study auroral Lyraes beyond the local group because they're too faint. Even in some galaxies where we can observe Cephids are much brighter, but we can't get the auroral Lyraes. Again, this is a single instrument program, so we've eliminated the systematics that would be introduced by using different instruments, because we're still looking at the auroral Lyrae with Spitzer with the same instrument in the warm mission. So this is some initial results from our program. On the left-hand side, we have period luminosity relations from the reticulum globular cluster in the LMC. On the right-hand side, you have a few examples of our light curves. And these, here we have auroral Lyrae, the archetypal auroral Lyrae star. We have UV oct and YZ cap. So auroral Lyrae actually has a parallax measurement from HST, like the Cephids did. And in this case, we have 5 auroral Lyraes with parallax measurements. And you can see in this, our exquisite light curves here, all enabled by the brilliant scheduling of Spitzer. We asked for what could possibly say unreasonable things by asking to look at these auroral Lyraes every hour or so over a day, and try and get as many observations in over one cycle of an auroral Lyrae. And you can see the periods here are less than half a day, and we're asking to look at it 24 times during that time. But the scheduling was really brilliant, and they could produce these amazing light curves. What you can see as well is that, contrary to the Cephids, the colour curves in this case are flat and are pretty much around 0. So we're not seeing the CO effect in the 4.5 micron band. On the left-hand side, on the PL relations from reticulum, is something that hasn't really been investigated before. In the optical, people would use the period luminosity metallicity relation, or the period metallicity relation, to measure distances to auroral Lyrae. But as you can see, if you take the run of PL relations through the B band to 4.5 microns, although the optical PL relations look pretty flat, as you go into the infrared, they do get steeper and the dispersion decreases, as with the Cephids. So there is a very useful PL relation for auroral Lyraes, and it can produce, the dispersion of these is around a couple of hundredths of a magnitude, 400 or 500ths of magnitude. So our uncertainty on a distance to a single object in say, a globular cluster or in the bulge of the galaxy is much more precise than it would be for a Cephid. So actually, auroral Lyraes are better distance indicators, but the problem is that we can't see them out as far as Cephids. So here we have an illustration from the Hubble survey, which shows the positions of 16,000 auroral Lyraes seen by Hubble. So Hubble took different images of the galactic bulge and then to look for gravitational lensing, but then they found all these RLI rays and just catalogued them. So now we can actually follow them up with Spitzer. So we can't follow all of these up with Spitzer, but we're following a selection, and that will allow us to correct for extinction because we have optical measurements and we have the mid-infrared. So once we can do that, we can make a 3D map of the Milky Way and really see the structure revealed by RLI rays. So the future is that we hope to go to 1% on the Hubble constant. The reasons why are what I said at the start of the talk. We want to understand dark energy and the curvature of the universe. Bringing the uncertainty on the Hubble constant down brings down the uncertainties on those parameters. It's going to tell us things like the mass of neutrinos. How many neutrinos are there? It's something we still don't know. But the problem we have right now is illustrated by this plot on the right-hand side by Zaritsky. We don't have many galaxies that host more than one distance indicator. Sometimes we get lucky, like we have galaxies that have Cephids and eclipsing binaries or RLI rays. But it's going to be very, very rare that you see a galaxy where you can measure RLI rays and a supernova, or even Cephids in a supernova. So what we need is to find more galaxies with more of these distance indicators. We also need to work on the theory behind these indicators. That could be one of the problems, that why we're getting different measurements of geometric distance is that our theory isn't right. We need to work on Cephid theory and supernova theory to reduce the systematics in this part of it. We also have different techniques we can try. There's things such as surface brightness fluctuations, which are looking very promising, and maser galaxies. We need more galaxies with masers and Cephids where we can combine the geometric and the luminosity distance. So what we really need is more systems with multiple indicators. So I'll just give a brief introduction here to one of the things that a colleague of mine, Mansi Kasliwala, is working on, also with Spitzer, is the dynamic infrared sky. So this is the picture of what the variable sky looked like a few years ago. We had classical novae, core collapse supernovae, and thermonuclear supernovae, and nobody knew about anything else. But in the last few years, a whole host of new transients have been discovered, and a lot of these using Spitzer. So an interesting section of this plot is the intermediate luminosity red transients and the luminous red novae, and some of these were discovered using Spitzer. So one thing you can do is go through the archive of Spitzer to look for extremely red variables that you wouldn't notice using, say, optical data. You can find these extreme variables that are on the right-hand side of the plot. And a new survey that's been proposed is SPIRITS, the Spitzer Infrared Intensive Transient Survey, which would be a systematic search of 242 nearby galaxies with different cadences to pick up different types of transients, and would also have optical and near-infrared surveys at the same time to complement the data, and near-infrared and optical spectroscopic follow-up. This was proposed for Spitzer Cycle 10. And this will complement things like the CHP. With a systematic survey of galaxies, you're going to pick up more supernovae and more transients that we can use as distance measurements. And maybe even new variable stars that we hadn't seen before. So by combining these seemingly different surveys, we can advance the science in both cases. So in summary, over the last 4 years of the WARM mission, the CHP has been working on measuring the distances to local galaxies in the Hubble constant. We have a very accurate measurement of the distance CLMC, and one of the most accurate measurements of the Hubble constant to date, with a systematic uncertainty of 2.8. We've confirmed this with a measurement of the Hubble constant using the Tully-Fisher relation, also with Spitzer. And thank you to time-resolved surveys with Spitzer, we can reduce remaining systematics even further.